Auto, yes. I definitely did a bunch of auto. Yeah, that counts. You can do that. So a while ago in class we were doing some induction on trees, and we proved a theorem about the size of a flattened tree. And so I want to prove that in Agda. And along the way we're going to see some other things that Agda can do. A little more complicated example. So rather than do it all completely from scratch, I've put some stuff in here to get started. So so we're not using our own natural numbers anymore. We're using natural numbers from the standard library. But this is how you import only a few things from a module. You can say using and then list the things that you're using. And then we imported some things from data.list. This is the equality, the like triple equals thing, right? And then this is, we'll see what this is in a minute. And on the homework, you'll see that there's I have a bunch of imports there. Here's specifically the things that you can use from the libraries. We'll look at this later. I'll show you what that is in a minute. So we've already proved in class that plus is associative. I just repeated that here because we're going to need it. And so rather than reproving it again, we'll use it. Here is a definition of a binary tree. Okay, this is standard, very similar to what it would look like in Haskell as well. Right, so a tree is either empty or it's a node that has left and right subtrees and a value of type A. And then we have our flattening function that takes a tree and flattens it into a list, right, by saying, the empty tree is an empty list, and if you have a tree with left and a value and a right, we just flatten the left and then singleton thing in the middle and then flatten the right. Okay, and then we define the size of a tree just like this, right? Empty tree is 0, has 0 size, and a node, it's 1 plus the size of the left plus the size of the right. Okay, and then I believe the theorem that we proved in class was that if you flatten a tree and you look at the length of the list that results, that's the same as the size of the tree. So we'll call it flatten size, maybe. And we want to say, well, for all types A, and for all trees, right, so for any T that is a tree A, it should be the case that the length of flattening T is equal to size of T. Okay. So, let's prove it. Now, we could proceed similarly to, we should certainly proceed at first similarly to what we've done before. So what's the very first thing we should do? Pattern match on T. Good. This should be automatic, right? Just pattern match on something. That's always how it starts. Okay. So line those up because I don't like it when the equals aren't lined up. And make this a little bigger. Okay. My goal is to prove that length of the empty list is equal to 0. Can I do that? It's probably, yeah. And this is one of those things where, if I tell it to reduce harder, if I do control U, control C, control comma, it's like, oh, okay, length of empty list, that's actually 0. It's just by definition of length. So that's just reflexivity. This one is going to be a little more challenging. It picks terrible names, so I'm going to change the names of things. That's the one downside of when you have it do pattern matching for you. It just tends to pick terrible names for things, for the variables. But you know what? Actually, I don't remember if this works or not. Let's just try it because I don't remember. And if you do this, there's no need for me to put names on those because they're not used later in the type. but I'm wondering whether doing that will give it a hint to choose those names. If so, that would be neat. Reloaded it. Nope, that doesn't. All right, so forget that. Okay. Okay. So this is, it's not even obvious what to do here. But I think last class, I think it was Andrew who said, so when we're doing these proofs that are similar to proofs that we've done on paper, like should we be following the proof that we did, or do we just kind of let Agda guide us? And for those proofs we were doing last time, they were simple enough that we could pretty much let Agda guide us, and we just say, hey, what do we have to prove? Oh, I can see how that's going to work, right? But there's going to be multiple steps here. In particular, I think we're going to have to use, multiple equalities, and then use transitivity to kind of stitch them all together and say this is equal to this is equal to this is equal to this, and then eventually I show that it's this. So it's really, really tedious if you literally type trans of blah of trans of blah, like you're making this giant, huge thing using transitivity. So there's something way cooler that we can do, and this is what this thing is here. This equality reasoning module. I'm going to show you how it works, or how we use it, and then I'll actually show you how it's defined. And it's super simple. So I type begin, and just a second. I'll tell you what these are in a minute. Oops. Okay. So what is this? I can write a proof of an equality by, I can say begin, and then I have the thing on one side of the equality, and then at the end I have the other thing, that I want to prove it's equal to, and then I make this little symbol to show that the proof is done. This is, you can literally type \QED, makes that little symbol, and then in here I have to give the reason, a proof that these two things are equal. Okay, now so far this doesn't help very much, because this is exactly what I had to prove in the first place. But the point is, I can actually chain multiple ones of these together. I can have a big list of these, and then in between each one I can give a proof that those are equal. And it's going to stitch all these together using transitivity and give me a proof of the whole thing in the end. Okay, so one way to approach this is to say, all right, let's forget about what Agda is telling us. Let's just think about, what would be the first step we would make if we were doing a proof on paper. And you know what? It might be easier if we, that's actually the literal definition of flatten. It was just doing a little bit of reduction already. But I think it'll be easier to think about if we don't do that. And if you don't want it to, so see how it's doing that reduction here? If you don't want it to do the reduction, right, you can do Control U once before you ask it for the goal. So you say Control U, Control C, Control R, and it's still doing it a little bit, right? Because it's, instead of writing X in the brackets, it's writing X cons empty list, which is of course how you make a singleton list. But so we could say, well, okay, what we need is and if you remember, we did this in class, we need a lemma that says, if you look at the length of some list plus another list, it's the same as the length of the first one plus the length of the second, right? And if we could prove that, right, for example, and so here's what I usually do. I copy and paste those two lines, right, and then I paste them, and then I just edit this line to make it into what I want it to be. So I want this to be this plus the length of that. Innocent, you look concerned. What's up?
So it looks like here you are trying to break these two things of proving going inside on how they are previously defined. Like, for example, the first one, length of flatten L plus X plus flatten R.
Yep.
That was like our recursive case in our previous formula of length.
Yes, that's right.
Like, why are you like trying to restructure these formulas and then sort of proving them from inside? Like,
I mean, ultimately I'm trying to prove that this first line is equal to this last line.
Okay.
And I'm going to do it by a series of steps. Right? I'll say this, I'm just going to make a tiny step. This is equal to this.
Mm-hmm.
And then this is going to be equal to something else. I'm going to keep inserting more steps until we finally get to that last thing that I want to show. Okay? So, and we have to fill in like the reasons over here why these things are equal. So this first step, right, is actually a lemma that we have to prove. Right, that the length, if I concatenate two lists and look at their length, the total length is the same as if I had looked at the lengths of the individual lists and then added the lengths together. So let's prove that. We'll call it length plus plus. So I want to say for all types A, for all, I guess I need to talk about two different lists. So for all lists x's and y's, the length of x's plus y's is equal to, I'm going to move this down here so we can, is equal to the length of x's plus the length of y's. Does everyone believe this lemma is true? Does it make sense intuitively that it should be true? Okay. So, let's see if we can prove it. If I say, how should I start? What do you think? Pattern match on x's, yeah. Ivy, were you going to say that? Or?
You have to do something like with the transitivity.
Transitivity of what?
Of size or length.
I don't know what transitivity of length means.
You mean like it's distributed? Yeah.
Well, that's what we're trying to prove.
Yeah, that's kind of what we're showing, that length distributes over plus. Like, well, with respect to a different plus.
Oh, I thought we already proved distributed.
No, I don't think so. Well, we proved this in class on the board.
Okay.
We have not proved it in Agda.
Okay.
So, yeah. So, we're going to pattern match on x's. Another way to say that is we're going to do induction on x's, right? Assuming we're going to make a recursive call. So, oh no, let's. There we go. I don't know. Does that look true? What do you think? Yeah, if I tell it to reduce harder. Yep, those are the same, right? And I could also just try. You can always just try doing auto, and if it works, then great. And if it doesn't work, then you think harder, right? If you're defining a function like that's going to compute something, then don't use auto because it's probably going to do the wrong thing. Like we saw that when we were defining map the other day. But if you're just trying to prove something, then as long as it finds a proof, you don't care. And so if it can find a proof at all, then you're doing great. I don't know, let's try auto. Oh great, it works. Okay, I mean, you know, we could think about it a little harder if we want, but if I tell it to reduce harder, is right, successor of something equals successor of something. Right, because right, the length of x cons x's is 1 plus something. And so I get that 1 plus on both sides, and then I can just say, okay, use cong, right, to forget about the suck. I just want to show that these inside parts are equal. But the inside parts are literally just the induction hypothesis. Right? So that's why we're getting that. Okay, so now we can go back down here and say, well, now I want to use that lemma to show that, right? So notice the goal is I have to show that this equals this, right? That this line equals this next line. So then this should just literally be an application of that lemma, right? because this looks like length of something plus something equals the length of that plus the length of the other thing. So if I say auto, I think it's not going to work. So if I say Control C, Control A, it says no solution found after 1,000 milliseconds. I don't know why it shows it in milliseconds. However, well, let's give a proof explicitly, and then we'll talk about how you could do it a little more automatically. So I want to use length plus plus, right? Length plus plus is going to give me exactly the kind of equality I want. But length plus plus needs two lists as arguments. I need to tell it which two lists I'm talking about. And so those lists are, the first one is flatten L, right? Because that's this first thing here. The second thing is, right, this list here. So I can it accepted it, so it works. Okay, I think I can also, let's just put this back. I think it's enough to just give it a hint and say, hey, I would really like you to use the length plus plus lemma here. So type length plus plus and then do auto. So I do Control C, Control A. Now it means it's willing to use that. Normally it wouldn't. It's not just going to use random lemmas that I have floating around. But if I give it a hint and I say auto, it's like, okay, I figured out how to use that lemma to prove it. Right, because basically it says, oh look, I noticed that lemma you gave me a hint about, like the output type, or the thing it returns has the right shape. So now I just have to figure out automatically what I could put in the holes, and it kind of keeps doing that until it solves it. Okay? All right, well, what do you think would be the next step? What should we show this is equal to?
Length of flatten L plus length of the list of just x plus length of flatten.
Yeah, exactly. So we want to basically apply that lemma again on that inside part. I still have length of something plus something. So I want to show, I don't know if I need parentheses there, probably not. Let's make sure to be kind of careful about parentheses, because even the fact that plus is associative, we have to explicitly use that fact, right? It's not just going to let us put pluses where we like. And in particular, I think actually that plus associates to the left. So if I didn't put those parentheses, it would be wrong. It would not let me prove it, because without the parentheses, it actually groups the length flatten L and length x together, right? But I want the x and the flatten R to be grouped together because, oh, I should have said length flatten R. There we go. Now do I have too many parentheses? There we go. Okay. And let's prove this. Now, I can't just directly say length plus plus, because the fact that this line is equal to this line does not literally match what this theorem says, right? This doesn't look like length of something plus something. It's some stuff plus length of something plus something equals that same stuff plus length of this plus length of that, right? So anytime that you've got some equality and you've got some stuff that's not changing and you just want to talk about the inside stuff, right, that's Cong. We want to use Cong again. And so I can say Cong right, and now I have to give it the function that I'm applying to both sides of the equality, right? So this says make a function, we'll call it, I already have something called R, so I'll use R. I'll use, I don't know. Okay. And this function says, basically I'm saying once I've proven that length of x plus flatten R equals length of x plus length of flatten R, what function do I apply to both sides to get this equality that I want? And so that function is, well, you do length of flatten L plus whatever that thing is. You know what? We can move these over. I just realized I like putting them, like having these way over here, just because it makes it easier to read, but except when I'm on the screen that's, only this wide. Maybe we should actually move them over like this. Maybe we can put some blank lines. Will help us read a little better. Okay. So, all right. And now, after doing Kong, right now I just have to show that that inside part is equal, but this inside part is just the length plus plus lemma again. So length plus plus. Wow. It says ruffle. So apparently, all right. I guess because we wrote it in terms of plus plus, but really it's a singleton list plus plus something, and that can reduce to x cons flatten r, and then length can reduce on a cons to 1 plus flatten r, and so it actually...
On the next line, can you just say like 1 instead of length?
Yeah, we could. I'll do another step just for that to show. I think we can do length plus plus here, but apparently this whole, that's fine. So we don't even really need the Kong, actually. We could just say ruffle for the whole thing. That would be fine. Yeah.
Could you explain why I used Kong in the first place?
Yeah, because I thought, okay, because if you look at, I'm trying to show that this is equal to this, right?
Yes.
And I can do that because we have a lemma that says that this part is equal to this part.
Yes.
Yeah? And so then Kong says, I'm going to take the equality from between this and kind of lift it to an equality over this whole thing, because this part doesn't change. Right? So whenever you kind of do the same thing to both sides of an equation, it stays true. Right? And so I had this equation that said this is equal to this, and I'm going to do the same thing to both sides, which is to add length flatten L to both sides. Right? That's what the Kong is saying. It says, hey, if Kong says, if you do congruence and you take each side and you add length flatten L to it, right, then you just have to, now I just have to prove that this equals this.
Okay.
But it turns out, right, because this part actually is a singleton list plus plus something, that reduces a lot, and it actually can just see those are equal without needing the lemma. All right, well, this now, and so Eric was saying, oh, length of singleton list of x, that should just be 1, right? And, oops, I think I have an extra parentheses. Except, oh, I know I do need these parentheses here. Right, why is that? Why is length of singleton list of x equal to 1? It's just by definition, right? Like if you just say, okay, definition of singleton list is x cons empty list. The definition of length on x cons empty list is 1 plus the length of empty list, which is the same as 1 plus 0, which is the same as 1. Like it can actually just unfold all those definitions and do that. So we don't actually have to say anything here besides ruffle, right? Because it can just compute both of these and see that they're the same. And in fact, this is a fairly common thing where you like, for my own sake, right? For my own ability to read it, plus the ability of anyone else to read it, I want to explicitly record the fact that these two things, is like a step. But actually, Agda can just unfold the definitions and see that they're the same. So, in fact, there's an abbreviation where it just provides this operator that just doesn't, you don't put anything inside of it, and that just means these are equal. These are just the same. So this is an abbreviation for ruffle.
So could you leave that step out like entirely?
Yeah.
It would guess like
skip that entire thing.
Yeah. Any reference step you could leave out entirely. But typically, if you leave out all the reflexivity steps, the resulting thing is tends to be pretty unreadable, because like as humans we can't do all those steps in our head that quickly and see that like this is really the same as this by definition. Because it's like applying all the definitions at once and doing lots of steps of computation, potentially. Okay, what next? Getting closer. So why is this equal to this? Or what might be another step we could do?
I'm
Yeah.
also gonna show how like length of flattened L is equal to size L and length of flattened
Yeah.
R is equal to size
Why
R.
is that true?
Hmm?
Is that true? Andrew?
It should be.
Yeah, should be.
Yeah, it should be.
Why is it true?
Induction hypothesis.
That's our induction hypothesis, exactly. And in Agda, we can use our induction hypothesis by just making a recursive call to the function that we're defining, right? And the reason that counts as an induction hypothesis is that it'll only let us do that on things that are smaller, on things that are sort of sub-things of the original thing, and that's what induction says. It says, hey, if you get to assume that it's true about these sub-pieces, you have to show now it's true for the whole thing. So sure, let's do that. So this should be equal to size L plus blah, blah, blah. And I'm not going to do these one at a time. I mean, there's other ways you could, for example, prove a little lemma about plus and say, hey, if A equals B and C equals D, then A plus C equals B plus D, right? And then you can kind of like change something on both sides of a plus at the same time by giving a proof that the left sides are equal and a proof that the right sides are equal, and then we wouldn't have to do this in quite so many steps. We wouldn't have to use Kong so much. But just for simplicity for right now, we'll do it like this. So this is going to be, well, again, I have to use Kong because, right, this part now is the part that's not changing. So I need to say, K plus 1 plus length flatten R. Right, and now, whoops. What did I do wrong? Reload, maybe? Oh, there we go. I hadn't reloaded, that's all. And this is just the induction hypothesis, right? So I can say, well, in fact, if I do auto, it'll figure that out. In fact, I wonder, it might actually, if I just do auto for this whole thing, it figured it out. Although it wrote it in a terrible way. But let's put ours back. I like ours better. Right, because it like had replaced the definition of length with some kind of fold, like length is defined in terms of fold R, and you see that showing up. But yeah. Okay, and then let's do the other one, right? So this should be size R, right? And this is going to be Kong of lambda k size L plus 1 plus k. Right, the argument to the lambda is like picking out the part that's changing, and the rest is the part that's not changing. And of course, that's just going to be flattened size R, the other induction hypothesis. We are almost done. Are these the same? So they're not the same. I can't just do ruffle. Right? What do I need?
Is it
Associativity, right. Yeah, so this is really like plus associates to the left, so when we write the plus without parentheses, it really means this. So maybe I'll write it explicitly just to be clear. And notice I reloaded it and it accepted this, so it has accepted that this thing I wrote here is the same as, you know, the right hand side of whatever we were trying to show. So I just need to use the fact that plus is associative, right? So if I say plus assoc, and plus assoc I think takes 3 arguments, which are the 3 numbers that were, so size L, 1, and size R. Alright, if I say, it says error. What the heck? Anyone catch what I did wrong? Might have to scroll up a little bit. Here. There we go. Yep.
This error says size L plus 1 is not equal to size R, size L.
Mm-hmm.
I am assuming there is probably some wrong comparison you're doing in terms of what things are comparing.
Yeah.
You just need to reverse L and R.
Reverse
swap
L
the
and R.
position of them.
What do you mean? Oh, you mean like put R here and L here?
Yeah.
Okay.
That's
Nope.
The problem, I think, is that up there you have that, like, well, is triple equals reflective itself? Like, does it know
You mean
that
symmetric?
Or yeah, symmetric.
It is symmetric, but like
Does it know that?
no.
Because like you have the first thing that you know is x plus y in parentheses, whereas down here we have
Right.
parentheses on the right.
Exactly.
And want to move it to the left.
Yes, this is exactly why, right? And I made this mistake on purpose so that you think about this, because, right, the fact that plus is associative, it literally says if you have something that looks like parentheses x plus y plus z, that will be equal to this other thing. But here we're trying to show it's flipped around the other way. So we have to explicitly use the fact that equality is symmetric to flip the equality around the way that we want, right? Because otherwise it doesn't match. So I do want L and R like this, but I can just say sim of that. So I think we proved this a while back, but there was a function called sim that just takes an equality between x and y and gives you an equality between y and x. So if I apply it to that, that should work. Yep. Questions? Other questions? So let me show you how this is defined. So if we go look at the Agda standard library on GitHub. Oh wait, no, I actually have a link to it right up here. So let me make this a little bigger for you. So this is the way that right, how we were able to write begin, something equals something equals something, QED. This is how it's defined, okay? So there is a function called begin, which takes a single argument, and it's just the identity function. It says, hey, if you give me a proof that x equals y, I'll give you back the same proof. Really, the only reason begin exists is to help with parsing, just so that it knows, like, oh, this is a proof that's starting. And then this QED thing, right, just takes a single argument and turns it into a proof of reflexivity for that thing. So if the last thing in your proof is like, some expression, and then you put QED after it, that turns into a proof that that thing is equal to itself. Okay? And the reason for doing that is that the important point is this equality symbol, Not this one. That's not the one. No, that's just the one that has reflexivity. This is like what happens when you do a single, something equal to something, and you give a proof of it. It says it's just transitivity, right? It says before you had a proof that y equals z, and then inside the where you say like this is the reason why, that has to be a proof that x equals. Wait a minute. X equals y. No. That the y equals z is what goes inside in the reason for something, right? X equals y is what you had before, and then the whole thing becomes a proof that x equals z. So I don't expect you to look at this and be able to follow exactly all the details. The point is just it's really, really very simple. All it is it's a combination of the fact that Agda allows kind of some fancy syntax, right? So like it says, hey, this syntax where you have like it's a 3-place operator, right? You have a first argument and then this symbol and then another argument and then this symbol and then a third argument, right? That just turns into a call to this step equals function. And the step equals function is really just transitivity. And then the QED symbol is just reflexivity to end the proof with, an equality. And then the begin just doesn't really do anything. That's it. So all it does is just like some nice notation that takes all your proofs and chains them all together with transitivity. I show you this as an example of you can actually have some pretty neat notation for things using Agda's ability to to define these arbitrary operators with arguments in different places. Apparently there's actually a version of this that uses this little, I don't even know what that is. Like in our last step where we had to use symmetry, right? You could instead use this version and it will kind of do the symmetry for you, right? So here it's defined by doing sim first. I didn't actually know about that. I think that's new in the latest version of the library. I don't know, we could try it just for fun. Let's try it. Because actually this will give me an opportunity to show you something else too. So let's comment this out and we'll say yay, checks it, okay. Now, one thing I want to show you, so this little thingy, how the heck do we type that? I don't know. Okay, so here's how you find out. You say Control U, Control X equals. And you get more information than you could ever want about this character. So it says, okay, how it's displayed. It's like, here's its Unicode character point. Here's the important line. To input, type \U curly braces with Agda input method. So you can try it. Say \U. Okay, there you go. So I don't even like what is it called? Does it tell us what it's called?
At the bottom.
Oh, breathe. Yes. There you go. So Control U, Control X equals to find out about a Unicode character. I mean, you don't have to use this. You could just use the sim, but yeah.
You see how we did this proof by kind of destructuring the length part towards the gravitating to the size of t part?
Yes.
If you had to prove the other way around, like let's say we wanted to say like size of like let's say using like starting with the tree and then end up with the length part, are we using the same process but on a tree instead of length? Or like this proof can suffice both cases?
So if you want to prove
Yeah.
the opposite, that size t equals length of Latin t,
Yes.
well, if I want that, I can just say sim of this, and I can just use this lemma. I don't have to do this whole thing again, right? I mean, we could say, size flatten. If A is a set, T is a tree, A, size T equals length flatten T. Is that what you want? Oops, I have to use actual equals. Yep, well I can just say, let's make an argument T. I can just say sim of flatten size T. Yeah? I mean, we could do the whole proof backwards. That would work, but that would suck. We've already done it.
So does that mean if you're proving something, there's probably an easier way, and there's a difficult way, and it could be intelligent to use an easier way and then use sim to revert it? Would that be like
Yeah, I mean, yes, that's often true, that there's sort of a brute force way to prove something, and then sometimes there's an easier way if you notice some other tools that you have available that you can use. Yep. I don't know, so I wonder if can I just figure this out? Well, certainly won't if I just say auto, but if I give it a hint to use flatten size, yeah, see, then it figures it out. You just have to give it a hint about which lemmas you want it to use. So your homework, which is going to be doing some Agda proofs and stuff, is on the website. There are also some instructions on the website on how to get Agda installed, how to get Emacs and Agda installed. I tried to put together the best instructions that I could without going too much into crazy detail, but I have not actually tested them. Because I already have it installed. So please try, even if you don't start the homework, if you can try to follow those instructions and get Emacs and Agda installed before Friday, then we could probably spend some time, maybe a little bit of time, because I'm sure that some of you are going to get to work and some of you are going to run into problems, and then we can spend some time. Either you can come meet with me before then, or we could spend a little bit of time in class on Friday trying to get things to work. But I'm sure we're going to run into problems, and I want to help you all get through that so that you can actually do the homework. So.